is can the course of evolution be predicted? And today I'm going to want to investigate that question at the level of the genome and thinking about speciation. Or another way to think about it is to what degree is evolution contingent, that is, due to chance, versus deterministic, driven by natural selection and necessity. So one authority on this subject that weighed in was Stephen Jay Gould, who, through various ways to paraphrase, argued that if microevolutionary processes like Darwinian natural selection are really kind of limited in their prognostication power to a few generations at best, then maybe we need a different framework to try to understand macroevolutionary patterns and trends. I think probably all think that adaptive radiation might really provide insights into this question in terms of bridging microevolutionary processes with macroevolutionary patterns. And the reason I say this is that I'm thinking about it under sort of the ecological theory of adaptive radiations, that divergent natural selection is really important in generating at least the reproductive isolation that initiates speciation due to organisms shifting and filling open niches. And then if this is the case, then if you think about it, then ecological speciation may be responsible or play a role in a lot of the bifurcations that have happened during adaptive radiations, or even character displacement after speciation and secondary contact. There may be a role for natural selection, at least, in shaping macroevolutionary patterns to a large extent. Now, of course, that doesn't rule out a role for contingency in adaptive radiation, because there has to be available open niches for organisms to move into in time and space. And also you can think about capacity. There has to be, at least in an ancestral population, the capacity and ability to utilize those open niches as well. Right? So both of those are considerations. But still, if this is the case, then the natural selection is going to contribute deterministically to a lot of the patterns we see macroevolutionarily. Now, in terms of thinking about capacity, there may actually be trends as well in thinking about the genomics of adaptive radiation. And this is a recent summary from Berner and Salzberger, where they made these points that if we look at a lot of groups that have gone through adaptive radiations or have potential to go through adaptive radiations, if we could look into the future, they may have been characterized in the presence of a lot of extensive ancient variation, often diffused by gene flow in the population, right? And they may also actually have a lot of structural features of the genome, like inversions that facilitate the packaging of sort of multi-gene complexes into sort of mini units, right, of biodiversity that could then get shuffled around a lot to allow the capacity of an ancestral population to take advantage of a lot of open niches that are out there. So there actually could be still trends in adaptive radiations at the genomic level as well to allow the standing variation to be packaged and to be utilized then to respond quickly when open niches were built. So today I want to talk about this in Rhagoletis pomonella sibling species group, and I want to concentrate on three taxa. Rhagoletis pomonella, the ancestral hawthorn race of the fly here, and the Rhagoletis pomonella, the apple race, a recent shift about 170 years ago of hawthorn flies to generate this apple race. And another sibling species in the group, the Rhagoletis mendax, the blueberry maggot. And the idea here is that adaptive radiation in this group of flies is mainly due to host plant shifting and subsequent ecological adaptation. A lot of it has to do with life history variation and diapause life history variation to adapt to the phenological or fruiting kind differences of these different plants. So to summarize then, we really want to move across the speciation continuum from the host races here, hawthorn and apple, that are partially genetically differentiated and partly reproductively isolated from one another. Across this continuum of speciation over to Rhagoletis mendax, which is more fully genetically differentiated from the races and more fully reproductively isolated, to see if we can make any predictions about the underlying patterns of genetic differentiation from standing variation, let's say, in the ancestral Hawthorne race. Does it allow us to predict patterns of genomic differentiation when we go to the races and we go to that sibling species, and paying particular attention to standing variation that exists in diapause life history variation? And the reason we are interested in diapause of life history variation, again, is because these flies all attack different host plants that fruit at different times of the year. The flies are univolting, they don't live that long in nature, so they have the time. In this case, we'll concentrate first on their eclosion times to come out as adults when the fruit's available, so they can mate on the fruits and then lay their eggs in the fruits. So that's really critical. In blueberries, the host of mendax fruit earlier in the season, then you get apples as we go in later, and then hawthorns. So their eclosion time correspond to the phonology of the fruiting times. Blueberry flies first, apple flies second, hawthorn flies third as we go earlier to later. Okay, so there's another part of the story of the history that you know of. And this relates back to that earlier Berner and Salzburg capacity or capability of adaptive radiation. And actually there's ancestral variation, gene flow, and inversions in Rhagoletis palminella. And part of the story is that maybe a million and a half years ago, the Hawthorne population at that time got split into northern and Mexican isolates. Conversion polymorphism was probably established at that time. There was then secondary contact and some gene flow that established a latitudinal decline in inversions from north to south in the ancestral Hawthorne population. And we've always hypothesized that variation in the ancestral Hawthorne population planted a seed for subsequent host shifts within this group to various different host plants that fruit at different times, including Rhagoletis mendax on blueberries and the recent shift from hawthorn to apple. So here's the general strategy and idea behind this. Let's do a GWAS bulk segregant analysis of eclosion time in the ancestral hawthorn population, right? Let's genotype the earliest and the latest quantiles of flies in that eclosion curve. Take those rads, and a little over 50,000 of them, and see how well it predicts the levels of divergence between the hawthorn population and the apple race. And then see how well it predicts the difference between the hawthorn race and the blueberry maggot at the species level. And we expect to see that trajectory somewhat being the same and more extreme as we go out to the blueberry fly, because they actually close earlier than apple flies, right? Make sense? Well, we did it. Here's where the largest responding rad loci kind of map to. So they're shown in orange. The orange are rads that show greater than 20%, 0.2 frequency difference between early and late closing hawthorn flies. And as you can see, this is an LD plot. So the things that are in this network here show high levels of linkage disequilibrium, the rads with one another, which should signify the inversions, right? And as you can see, the big responding rads map to what looks like 3 different inversions, mostly on chromosomes 1, 2, and 3 in the fly's genome. 5 major chromosomes, 1 dot. Okay, here's the meat and potatoes. Eclosion time, rad frequency difference along the X, and on the Y, the host race difference for chromosomes 1 and 3. Wow. And the orange are the inversions, or the rads that we think are showing high LD with one another that go to those inversions. And there's a real nice relationship and predictability there. Well, does it go over to the species level then? That's the key question. Right? Here's the difference between the hawthorn race and the blueberry Rhagoletis mendax. plotted against the eclosion time differences within the Hawthorne race. So the Hawthorne race has a standard variation. Is it partitioned then out to the blueberry fly too with respect to differentiation between species across the speciation continuum? Yeah, it is. It's not quite as tight, right? And the orange again is those inversions. So we see the same general pattern. There is some predictability there in the relationship. And it's more pronounced, as you would expect. There's bigger frequency differences in the blueberry comparison. What about geographic variation within the Hawthorne race? Because I said there were convergence lines in the Hawthorne race. That was our hypothesis. That was ancestral. That was then used to help generate some of these other, right, sibling species and races. So what I have here is a eclosion time difference in early late for a Hawthorne post-race, right? And what we plotted it about against is geographic differences at a site in the north and a site in the south. Grant, Michigan, and Urbana, Illinois. And what you see is a real nice, again, relationship, north-south, for those SNPs that's related to eclosion time. And here is actually the phenotypic measurements of eclosion time in these flies. Hawthorne race, you go from north to south. Yes, indeed, the flies within a race come out later as you expect. And the difference between the Hawthorne race and the apple race is consistent across site, but it's kind of sliding latitudinally. So far, so great, huh? Okay. That was a fast one. It's only a fast one. This is a discriminant analysis of the principal components, right? And so what you see is, here's the Hall earlier closures, here's the Hall later closures in our GWAS. You train the discriminant function on it, and let's plot out then the races and the species against that. And, oh, it looks really nice. Okay, Hall race, yeah, right. Apple race, the trajectory is all great. Mendex, blueberry flies, beautiful, except for one thing. Wait, look, this is the Hall later closers. I said blueberry flies come out the earliest and apple flies. So it's reverse, actually, when you get down to the nitty-gritty details at a given site. So what's going on? Well, it turns out that it might not be eclosion time that's directly being selected for. It may be another aspect of diapause, and that is if these flies are exposed to high temperature conditions for too long, they become non-diapausing and they come right out and direct develop, and those guys are dead, a low fitness out in nature. And blueberry flies come out before, apple flies come out before hawthorn flies, so those pupae that are blueberry have a longer period of winter before a long period as pupae in the soil before winter comes, higher temperatures. So it actually is probably that aspect with calcitrans to non-diapause development that's under selection, not the eclosion time. And when we look here, here's the phenotype. You can see going from north to south, in fact, the relative proportion of non-diapausing falls. Apple race has less non-diapausers than the Hawthorne race, and Mendex is even more recalcitrant to non-diapause development. So it's actually a different aspect of the life history, of the diapause life history that's directly under selection here, not the eclosion time for these particular markers. So this is just to show you that if we go back to our old experiment, we look at eclosion time differences, and then we do the same kind of bulk segregate for non-diapausing versus diapausing flies in the Hawthorne race, we see a real nice relationship again. So it could be pleiotropy or linkage that's causing that sort of counterintuitive relationship between eclosion time and the differences between the races and species. So then what's causing blueberry flies to eclose earlier? Well, let's do a bulk segregate analysis, early-late eclosion on blueberry flies and see how well it predicts the patterns phenotypically out in nature. And so that's what this is. Here's Mendex earlier closers. Here's Mendex late closers. Discriminant analysis again. And look, Hawthorne race, apple race, blueberry flies, They have the alleles, of course, closed earlier. Horace and Alvarez, actually, Rhagoletis palmella has alleles that predict, based on what's going on in Mendax, that they should have closed later than the blueberry clock. Where do these genes map? They map all through the genome. They're not concentrated on those inversions, actually. Which suggests the possibility, one, we had pre-standing variation in the Hawthorne race that helped facilitate the shift in the inversions, but it's possible that these genes represent newer mutations that may not be shared in Palmanella that allowed for the shift. So in general, in conclusion, yeah, we have a genomics of adaptive radiation for races and species. It's somewhat predictable. The standing variation of closing funds in the ancestral Hawthorne race seems true. But the selection is actually counterintuitive. Some of it is actually on initial diapause step. And then there's some other compensatory selection in Mendax to close earlier due to maybe new mutations that could, at the genomic level, be due to contingency. We need to sort of nail this down further. We don't know why apple slides are closed earlier yet. Is this true of other Rhagoletis taxa, and how sort of generally applicable to adaptive radiation is what we found here in Rhagoletis, but at least from the reviews from Berner and Salzberg, it might be sort of a common pattern as well. So thanks.